So we're looking at perpendicular bisectors for section 5.2. And so when we are talking about perpendicular bisectors, we have a theorem, and that is called the perpendicular bisector theorem. And so the perpendicular bisector theorem talks about points that are on the perpendicular bisector of a segment. And what it says is, if a point is on the perpendicular bisector, so if a point is on the perpendicular bisector of a segment, then it has a very special property. And so if a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. And we're not going to go through and write a formal proof for this, but it's important for you to understand what the proof is and what it consists on. So let's take us through this theorem and look at a picture of it. So we start with a segment, and then what we're going to do is we're going to bisect it, which means we're going to go through the midpoint. That's bisecting. And then it's going to be perpendicular, which means it's going to be a right angle. And that is the perpendicular bisector of that segment. We can call the segment AB if we want. And what this theorem says is, if we grab a point on that, so point C, then it is going to be equidistant, same distance away from the endpoints, which means the distance from A to C is the same as B to C. So to prove this theorem, we would need to show that AC is congruent to BC. The way that we do that is we say, oh, we know that it was a midpoint, so AD and BD are congruent to each other. We know these are both right angles because it's perpendicular, and right angles are congruent to each other. And then we get to use the reflexive property to say that DC is congruent to itself. So by side angle side congruence, those two triangles, triangle ADC and BDC, are congruent. And by CPCTC, congruent parts of corresponding triangles are congruent. We know that AC is congruent to BC. Now, there also is the converse of this theorem. And so theorem 5.3, which is the converse of the perpendicular bisector theorem. And what it says is just the opposite of this. And it starts with a point that is equidistant. If a point is equidistant from the sides of a triangle, from the, not sides of a triangle, from the endpoints of a segment, then it is on the perpendicular bisector. Okay, so again, let's break this down, and in the process, we'll get an idea of how you would do the proof of this. So this is, you've got a segment, AB, and then there is some point, and we're able to verify that this point is equidistant from A and B. So we know that AC is congruent to BC. So you're given this. So the proof of this is interesting because it involves constructing a segment, and you can actually choose, do you want to construct what's called a median, or do you want to construct a perpendicular line or an altitude? And so if we were to do the median, we would say, okay, draw in D is the midpoint. And then when we connect CD, what we need to show is that CD is also perpendicular. We constructed it so that it's a midpoint. We need to prove that given C being equidistant from A and B, if D is the midpoint, then it's also a perpendicular line. Well, the way you do that is proving those two triangles congruent again by side, 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 because we have three sides congruent in the two little triangles, which means this angle is congruent to this angle, but they're also supplementary. And so we know that if two angles are congruent, ADC, BDC, and supplementary, then they are right angles. And then by showing that they're right angles, that means that it is a perpendicular bisector, because we started out with it being a bisector because we can construct it that way. You could also construct it as an altitude, so it's perpendicular, and then prove that it bisects, and you would use hypotenuse leg in that sense. Now, one of the ways that this theorem, this converse, is super useful is it tells us and explains to us why the what we call the perpendicular bisector construction works. And so here's how the perpendicular bisector construction works. We pick one of the 2 points, and so I'm going to pick this one, and we draw a circle through the other one. And so that circle has a radius that is equivalent to the length of that segment. And then we do the same thing with the center at the other one. And we get another circle. And that leaves us with a couple of points that are on both circles. And so those 2 points that are on both circles means they are a radius away, which is the length of the segment, from the 2 circles. And so that means both of those points are equidistant, the radius, from the endpoints of the original segment, which means they are on the perpendicular bisector by the converse of that theorem. And that shows that that segment that connects those 2 points is automatically a perpendicular bisector. So the reason why this classic construction works is because of the converse of the perpendicular bisector theorem. And then finally, we could look at a problem where you'd use these theorems. This says BD is a perpendicular bisector. Well, what we know from that means that AB and BC must be congruent to each other. That's what the perpendicular bisector theorem says. If a point B is on the perpendicular bisector, then it's equidistant from the endpoints A and C. So that means that AB and BC would be equal. So we could say that 3x plus 7 equals 6x minus 17. Solve for x, and we get 24 equals 3x, so x equals 8. So in this problem, we use the perpendicular bisector theorem to know that those two are equal to each other, solve the equation, and we get x equals 8.